So we're going to finish up our first chapter today with the fourth section entitled Analyzing and Interpreting Data. So we've been practicing this over the last few days, looking at the Candle Lab and our Oreo Lab, right? And also with our alien activity, right? We looked into identifying patterns in the shapes and features of those aliens. So now we're looking into identifying patterns in a data table. And so you have two data tables. This first one here has, looks like 3 different samples of water, A, B, and C. And sample 1, or A, is 20 grams, sample B is 50, sample C is 100. And from the data table, it looks like what has happened is that I have changed water or split water into its component elements, the mass of hydrogen and the mass of oxygen. So my independent variable is what I changed, right? That's our definition of independent variable, what I changed. And the dependent variable is what I measured. So I look at the 3 different samples, and what I seemed to have changed is the amount, or in this case specifically the mass, of the water. And what I measured was the mass of the hydrogen and the mass of the oxygen that was formed. And my conclusions from this data could be a few things. The first thing that I notice is that I always form more oxygen, right? Always form more oxygen. But specifically looking at how this changes with the independent variable, when I used twice as much water, I made twice as much oxygen, and this one was hydrogen over here, and twice as much oxygen. So one way of generalizing a conclusion that I can make from this data table is that there's always the same proportion of hydrogen and oxygen made, right? If I look, this is, right, about 8 times as much. This is about 8 times as much. And if I double the water, I double the mass of hydrogen and oxygen. Those are the conclusions that I can make by looking at this data table. You have another data table on your handout. And from just looking at this data table, take a moment, you can pause the video and see if you can figure out what the independent variable and the dependent variable is, and then what conclusions you can make from this data table. Okay, so you have probably paused the recording and now you're back. You found that the independent variable, what I changed was the speed of the vehicle. Let's say it's a car, right? And then what changed as a result of that was the stopping distance. And what conclusions can I make from this is that if when I increased my speed, what also increased? My stopping distance. So when the speed of a car is increased, the stopping distance also increases. And that sort of makes sense to me, right? The faster that that car is going, right, the more energy that it has. And so it's going to take the brakes longer to stop the car. We can also look and figure out independent and dependent variable from a graph as well as a data table. When I look at this graph, the title is Atmospheric Carbon Dioxide. The independent variable is the year, and the dependent variable is carbon dioxide concentration. Remember, the dependent variable is what you measured. The independent variable is what I changed. Now, it's weird because I can't just change the years, but the years happened. That's what I'm looking at. I'm looking at the difference between 1860, 1980, 2020, and I'm measuring the carbon dioxide concentration. The independent variable always goes on the horizontal axis. Okay, so my independent variable is the year, and my dependent variable is carbon dioxide concentration. If I look at the units there, they're in parentheses. It's parts per million. That can be abbreviated with a lowercase p, lowercase pm, ppm. So then we have some questions that are as a result of looking at that table. So this is, again, maybe you can pause the video, try to answer questions 1 through 3, and then unpause the video and see how you did. So looking at this graph, right, in 1960, so this is 1960, right, what is the concentration of the carbon dioxide? Well, this little, right, line there is 310, so it looks like I am a little bit less than 320, but I'm above 310, right? Because this line right here is 310. So I said 318. And then the question asks us for the year 2000, and the year 2000 is up there. And when I look at the year 2000, right, that looks more like about 372. I don't know why it won't let me pinch down. So 1960, it was about 318 ppm. And in the year 2000, I said 372. Now, if you didn't exactly say 372, if you said something less or just a few degrees off, right, that's perfectly fine because, you know, we're doing our best at reading this table. How much did the concentration increase between 1960 and 2000? So I'm subtracting those two numbers, and so I get 54. Question numbers 4 and 5 are a little bit trickier. What was the average rate of increase over time? Anytime you see this word rate, right, it always means a change and then divided by time. So what was the change? So I'm looking for the change and increase of that carbon dioxide. So it increased 54 ppm over the time from 1960 to the year 2000 was 40 years. And if I actually do that division in a calculator, I would get 1.35 ppm per year. And this is a trickier question. That's why I'm not having you pause it and try it on your own. We're going to do it together. If the average rate of increase remains constant, so meaning remains that number, what would the carbon dioxide concentration be in 2030? So in the year 2000, right, we said it was 372. In the year 2030, so that means it will have been 30 years. So if it is increasing at 1.35 ppm per year, and I multiply that by 30 years, I should get how much it would increase by. When I do that out, I get the number 40.5. The unit of that is ppm, that it would increase 40.5 ppm over these 30 years. So I take in the year 2000, it starts at 372 ppm. I would add that 40.5 ppm, that would be the additional carbon dioxide added, and that is going to be, what does that come out to be? 412.5. So if the rate increases, if the concentration increases at the same rate, then in the year 2030, the carbon dioxide concentration in the atmosphere would be 412. This next question says, what is the average rate of increase in the carbon dioxide concentration between 1880 and 1920? So it's asking you to do basically the same thing we did in number 4, but over a different time range. So pause the video and see if you can calculate that. So I looked on the graph, and it seemed like in 1880, the carbon dioxide concentration was 298 ppm, and in 1920, it had only gone up to 304 ppm, which means that, right, the rate of increase, the change over time, was 6 ppm over that 40 years, or just 0.15 ppm per year. And that is a lot smaller than what we found in number 4. So then the question says, what might be the reason that that rate has increased? This should really say why. It's a typo on my part, I apologize. Why might that rate be different from the rate between 1960 and the year 2000? So think of some things, possibilities for why we as a society created more carbon dioxide between 1960 and the year 2000 and the year 1880 and 1920. I can think of 2 major reasons, and this is just to get you think. There's no real right answer for this, so if you didn't get one of these answers, no big deal. I would say number 1 is population increase. There was many more people on the planet in 1960 than there were in 1880. So just if every person made the same amount of carbon dioxide, we would expect there still to be more carbon dioxide. But the second one is industrialization. Industrialization is the idea that in 1880, there weren't very many cars, there were no airplanes, electricity. People didn't really have electricity in their houses. And then 1960, all of those were much more widely used. And with industrialization comes using fossil fuels. You probably heard that word before. It's a word that collectively describes coal, oil, and natural gas. And we use those fossil fuels, we burn those fossil fuels specifically, and extract the energy that was contained in them. That's how we make electricity. That's how we go from place to place with cars and trains and planes. And when we burn fossil fuels, one of the products is always carbon dioxide. And then the very last section is just, if you read this in your textbook, and if you haven't downloaded your textbook yet, you can. It may be easier to download it at home than in school. The author talks about what you need to be successful in chemistry. And the author points out these three things: curiosity, calculation, and commitment. And when I think of curiosity and commitment, I think about sort of this graph right here, this graphic, I should say, right here, that a good chemist is constantly asking the question why. And then after you answer that question why, you sort of get a new question, and you're looking for really a root cause of something. So think about the observation, water is a liquid at room temperature. Well, why is water a liquid at room temperature? And you guys know this from biology, that water is very polar. And so water is really attracted to other water molecules. And at room temperature, the attractions between the molecules are so strong that the molecules stick together. So here, the molecules are sticking together. Well, why do the molecules stick together? Because water's a polar molecule. Well, why is water a polar molecule? Because it's bent. The shape of that molecule, right, is bent. Why is the shape of that molecule bent? So we will learn it's bent because it has what we call, and you don't know this yet, so you should not know this yet, it has 4 electron domains around the central atom. Well, why does water have 4 electron domains around the central atom? Because water has 8, or oxygen, the central atom, has 6 valence electrons. Why does oxygen have 6 valence electrons? So you can keep going and going and going. And eventually we start getting into these, chemistry principles that we are going to start learning this year. So now you have enough information to finish up your homework packet, and that's what you should do for the rest of class. And if you have time left over, you can work on your Oreo lab. So your Oreo lab is due to be turned in on Monday, and I will check the rest of this homework packet on Monday.